Intanto benvenuti, welcome to everybody, and benvenuti al laboratorio. Questo non è proprio il laboratorio, this is not the laboratory, this is part of the museum which you have visited this morning. Se parla in inglese mi seguite? The museum that you have visited this morning, it's actually a unique museum in the whole world. It contains probably enough of a treasure to be able to save Greece from recession. As you have seen in the treasure trove, there are among the most beautiful instruments ever built. Some of them are 5 centuries old. Some others are only 3 centuries old, but those that are 3 centuries old are probably the most expensive ones. The 3 centuries old belong, in fact, to the golden period of production of violins, and we're talking about the early 1700s, when Antonio Stradivari started really changing the geometries of the instrument and getting to the point in which the sound would become particularly beautiful, and all the violins built here will be copied by everyone else in the world. We still are the center of the world here as far as the violin making is concerned, and hopefully it will become more of the center of the world as we go along in the future because of the many activities that are taking place in here. Finora ci siamo? Andiamo avanti? Okay. So, the Laboratory of Musical Acoustics, you have slides in Italian, so you can actually follow me in both languages right now. The Laboratory of Musical Acoustics is something very unique in many ways because it's inside the museum and along with another laboratory, which is the Laboratory of Non-Invasive Analysis on Materials. And so we have chemistry, we have material analysis, we have acoustics, we have vibrations, we have timbral analysis, so timbral qualities of the sound, we have machine intelligence, quite a few things that are put together in the same space in order to extract information that otherwise would be very difficult to extract. If I asked you, how would you describe the sound of a beautiful instrument? What would you say? What kind of words would you use? You use words probably like, oh, it's a mellow sound, it's a soft sound, it's very bright, very aggressive. You use a certain number of words that belong to your own vocabulary, correct? But you would never say that the directivity pattern is directed in that, very technical terms. You wouldn't say that. You would use terms that belong to everyday language. And this would help you convey what you expect from the musical instrument. Now, in order to do this, to be able to talk about a musical instrument in terms that are understandable from your standpoint and from the standpoint of scientists, we need to be able to manage the language, to understand, to formalize the language, and objectivize what otherwise would be considered subjective. So something that belongs to your perceptual experience. So this is an operation that requires some machine intelligence and language intelligence in a way. And this is something that later will be discussed by one of the presentations that Francesco Setragno is going to give you. The other aspect that is very important to discuss is how the musical instrument produces the sound and how it projects the sound in the environment and how the projected sound interacts with the walls, with the enclosure that you're in. Because does any of you play a musical instrument here? Do you play a musical instrument? What do you play? Guitar, that's a very good example. What else? Piano.
The piano.
Piano.
Drums.
Nobody plays brass, nobody plays woodwinds, nobody plays like an oboe or a saxophone or anything like that.
Clarinet.
So especially those who play a violin or a particularly directed musical instrument, know very well that you need to be in a very good environment to be able to enjoy the sound that you're making. Especially, with the piano you don't have much of a problem. The piano is a big instrument and it produces a beautiful wide sound field, and you can enjoy the sound even if you are in a very dampened type of environment that doesn't reverberate that much. But if you play a saxophone, especially because saxophone projects forward, it's shaped in such a way that the projection goes forward, it's really a problem to be able to play it in, for example, an anechoic chamber. The room that you're going to see later on is muffling the sound, and therefore you can't hear yourself playing. So being in a good environment is very important to be able to enjoy your own playing. And when you enjoy the way you play, other people enjoy it too. It's very important to have this closed loop in the interaction. So there will be another presentation which is going to be given by Antonio Canclini here, that will be talking about how to measure how the energy is projected into the environment with a musical instrument that is being played by a musician during the performance. This is a very difficult operation that have never been attempted before, and here in this laboratory we have done it, and we do it every time we want to assess the acoustic properties of a musical instrument. And there is one other aspect that is very important to assess. There is another aspect that is very important to assess, is how a musical instrument sounds to the listener. So these timbre qualities, how do you judge them? Is the sound good? Is the quality, the instrumental quality, sufficient for us to be able to enjoy the musical instrument as a player or as a listener? So all these aspects, the timbre quality of the musical instruments are very, they're up in the air. They sound like they're very hard to describe and define in scientific terms, right? What kind of formula would you write down in order to describe how aggressive the sound of a violin is, or how metallic the sound of a brass instrument is? It's very hard. You don't know what kind of formula to write down. So one way to do that is to teach a machine how to judge, right? So we have learning machines that mimic the behavior of our brain in many ways. You have the so-called deep neural networks that mimic the structure of your own brain. We have solutions that are based on machine intelligence, learning-based algorithms that learn how to judge. So we can do that too, and this is used in this laboratory as well, to teach a machine to formulate a judgment on subjective terms that become objectivized by the machine and by the fact that they are trained by the opinion of many, many experts. So all these aspects come together in this laboratory, along with the information on material coming from the University of Pavia. So let me just show you very quickly, and then the presentations are going to go through the content a little more in detail. Ok? Devo dire qualcosa in italiano per rispiegare quello che ho detto? Siete riusciti a stare agganciati? Beh, fa piacere. So, we have a bunch of information that is extracted by a lot of sources. We have vibrometric information coming from little accelerometers placed on the musical instrument, and you will be seeing that in the laboratory later. When you go down in the laboratory, there will be, Francesco is going to show you how we extract that information. We have timbral acquisitions, and this is going to be discussed here because there won't be enough time to do a demonstration on that. We have acoustic measurements, and Antonio is going to show you how to extract acoustic measurement that describe how the sound interacts with the environment. We have measurements on the material. You're going to see it in the laboratory downstairs. A semantic description, how you use your words to describe a musical instrument. That is going to be discussed in the presentation of Francesco, right? Francesco, am I right? Then perceptual tests. Very important to ask many questions to a bunch of people and be able to feed this information into the algorithms that are expected to learn how to judge, correct? So that's called machine intelligence, training machines to learn how to judge, to formulate judgments on the musical instrument. Finally, the machine intelligence, which is apprendimento automatico right in the middle, that is the set of algorithms that learn from all this information altogether. Going on, so let me show you what you're going to see later. There is a little bit of information on how you acquire vibrometric information using accelerometers and other instruments that you will see later. And going on, with the same kind of measurements, what you try to do is to get a snapshot, like a picture, of how the surfaces of the violin body react to an action, impulsive action. So these are called the vibration modes. In Italian, modi di vibrare. The vibration modes describe all the geometries that will be produced by the vibration and will describe basically what kind of timbre, what kind of timbre qualities will be associated with that particular musical instrument. You can do that by measuring it, or you can do that by simulation. There are techniques called finite difference methods that allow you to simulate mathematically the behavior of vibrational behavior of a structure. So you use either boundary element solutions or finite element solutions, and you can use them to simulate on the computer and maybe predict the vibrational behavior of a musical instrument. This is an example of a prediction of a vibration mode of a soundboard of a violin. Then, if you have this information along with the 3D shape of the musical instrument, which is extracted using a special machine, laser machine, called the laser scanner, you can get a very highly accurate 3D model of the instrument on the left-hand side, and the precision of that model is in the order of like a few microns, 10 to the minus 6 meters of accuracy, so 1,000th of a millimeter. You combine that information with the vibration mode, and you understand how you can do some calculation to predict how the radiance is going to be, how the power is going to be distributed over space. So this can be done in simulated fashion in order to obtain that radiance pattern of the violin. But we like to do it a little better than that. We don't just want to estimate that information, we want to really measure it on the fly. And this is something that is going to be shown by Antonio, who was actually the person who worked the most on this kind of system. You can also reverse the problem and say, what if I have the pattern, because Antonio was good enough to be able to extract it, and I have the 3D model of the musical instrument, and I want to do reverse engineering and figure out what vibrational mode I have on the soundboard. That's a very good question, because instead of using accelerometers placed on the musical instrument, I want to reverse the process and figure out how the surface vibrates from how the sound field is produced. So it's an inverse problem. So this is kind of a fun thing to try, because it prevents you, it allows you to skip a very expensive and a very involving step that requires using very expensive machinery, like a laser vibrometer, Doppler vibrometer, or who knows what else. So these are all things that you might want to skip in the whole process. Are you still with me? Should I slow down? Okay, good. You're doing very well with English. Wow, you thought you did it, right? Good. So, I'm going to skip a few slides because I don't want to spoil the surprise that Antonio is going to be talking about. So close your eyes for a second. I have to skip the slides. And you're going to be shown that. But let me just tell you what people do, so this way Antonio will look even better. Before Antonio, so this is before Antonio, so there is before Christ, after Christ. Before Antonio, the era before Antonio, people were using, in the Stone Age, people were measuring the radiance pattern using all kinds of machinery. One of the machinery that was used was this. They were taking very expensive violins, mount them on very sophisticated brackets, and they were using robot arms in order to basically start the motion on the string. And definitely the sound that it was producing was very far from the concert that you heard this morning. Something that was very mechanical. They were using basically all kinds of devices for obtaining a vibration that would be repeatable, which wasn't, and as steady as possible. But of course, it was steady, but it was unnatural. There was also the possibility of measuring it with a system like this. A person would be sitting on a stool and being absolutely still without ever moving from there, playing the violin, basically moving only the right hand, the right arm, and that system will be able to make just one slice of the radiance pattern using a bunch of microphones in that position. Of course, you obtain a little more, and it's very low resolution, but it's not what the person is producing during a concert. You've seen the concert this morning, the person was moving a lot, because you need to be taken by passion, and you need to be transported by passion. If you don't do that, the sound doesn't come out right. You have to create a certain level of empathy with the musical instrument, and you ride that empathy, otherwise it will not come out right. So this is what we want to have. We want to have a diagram somewhere that describes how the musical instrument is radiating its energy around. This is something that people do and control. I have a cousin that is an opera singer. We had long discussions about this, and he says that he normally controls, with the position of the mouth and the jaw and everything, how the radiance is opening up with respect to the audience. And he moves the head and turns around in such a way to beam this energy towards the audience in a modulated fashion, so that the people that hear the concert will be swept away by this modulation, this spatial modulation. Do you think this is an unusual thing? It's not. Many musicians do this on purpose. Professional singers and professional violinists do this on purpose. Even Edoardo Zosi, who's a student of Accardo here in Cremona, he was a student, now he's one of the best violinists in the world. He came here to record several pieces on the Stradivari Cremonese 1715, and the first thing he said was, this instrument, if you really want to record this instrument, you got to place the microphone exactly there, where you are there. So you hold the microphone for a second, and he knew exactly that it was like 63 degrees northeast and an elevation of 23 degrees up. Can you believe it? Well, we tested that, and he was absolutely right. He knew where to point the violin, and that was quite amazing if you think about it. And he, not only did he know where the sweet spot of brightness was, he knew how to control it and how to move in such a way that the listener would be modulating, would have a modulating effect on the sound. How do you measure it? Well, ask Antonio later. So let me close your eyes. I'll go super fast so you don't see that. Another thing that's going to happen is about timbral analysis. You're going to be talking about the timbral analysis, so I'll skip that too, because that's kind of fun to see. And he's going to be talking about Luthiery ontology. Can you believe it? Ontology. Ontology is something that you probably hear in philosophy of science or many other topics, and but we don't use the word with that meaning. For us, the word ontology is basically is an engineering term. We use the ontology to describe a bunch of things together. For example, how close two terms, two words are to each other. So we place words in a metric space so that words like soft and round will be close to each other, but bright and aggressive will be on the other side of the range. So you have proximity and distance that describes semantic distance or semantic proximity. And you need this metric space in order to understand how to judge the words that you're using. You might say that the musical instrument produces a sound that is very round, and someone else might say that is a very soft sound. The two terms are actually quite different in meaning, but they're not that different. So you might use a little bit of the training that you used for the first word, and also to train algorithms to learn how the second word works. So you don't have to work as hard, because we have many, many words. In Italian, we have 125,000 words according to the Voto Ori, which are probably have grown a great deal. In the Webster, in the British Webster, it's actually an American dictionary, but there are over 1 million terms. Remember, the English language is a lot richer than the Italian language in terms of words. It's less rich in terms of structure. But if you are to train algorithm based on words, you have to be aware that there is a lot of work to do as far as training goes. On the other hand, the training can be shared among words if you use semantic proximity. So you can save in time. But it's not just that. It's basically the technology of semantic web. And I'm almost done because I'm stealing all of your time. Semantic web, have you ever wondered why Google tells you things that you didn't ask for? Sometimes you want to go to, I don't know, you want to go visit my violin museum and it's 7 o'clock in the evening, and you type violin museum and you ask for direction, and Google comes up and says, yes, these are the directions, but don't go because it's closed. Have you ever wondered how he does that? The information is actually inferred by semantic web. Semantic web puts together information that has little to do with each other and draws conclusions, trying to anticipate your needs. Now, how can you do that? You need to be able to manage through ontologic descriptions and this sort of things, what could be possibly useful to questions that you have an answer. You have an answer for questions that haven't been formulated yet. So it's very important for us to use the same technology in managing information on this sort of things. So maybe you can say more about that in a minute. And I think I'm going to stop right here. No, just one thing, because you're not going to be talking about rendering. Are you going to be talking about rendering?
We have a demo.
We have a demo, so let me say a couple of things about that. Have you ever wondered how to relieve an experience, a listening experience? So this is how we tape content. This is how we record it. We have quite a few, well, we have hundreds of microphones because we like to brag about it. And so we buy a lot of microphones because it's cool. How many microphones do you have? I have 2,000 microphones. No, that's not the way it goes. We have plenty of microphones, not because we like to brag, but because we like to use them all together. This is an example of a very special microphone called Eigenmic, and it's something that doesn't cost as much as a Stradivari, but it comes close. Okay? I don't tell you how much, but it was a pretty expensive thing. It's a ball of 8.4 centimeters with 32 microphones inside, professional grade microphones. The latest version has 128 microphones inside, all in a small ball of about 10 centimeters, but they're less those are MEMS microphones that are less expensive than these microphones. Anyway, so this ball, we use it to capture the entire sound field. Actually, you don't capture the entire sound field. With the ball, you capture 32 channels. That's it. And then there is Antonio, because he's our hero of the day, who takes care of crunching the data and producing a 3D sound field coming from there. Okay? So there are mechanisms that allow you to represent signals in a very complex representation space. Do you remember the integrals? Oh, you are all students of high school, so you are probably fresh with chemistry, are you? Just tell me you remember chemistry. You can't be here without knowing chemistry. You're okay, you do remember. All right, so since you remember chemistry, you probably have seen functions that look like this, haven't you? Does that remind you of anything? Those functions are called they're called Schroeder. No, are they called Schroeder? I don't remember.
Schrödinger.
Schrödinger. There is a Schroeder integral. It has nothing to do with this. There are the orbitals, the Schrödinger orbitals. So this is a representation of the orbitals. It's the probability of finding an electron in a certain area. Wow, have you ever wondered how they were found? You certainly were using a microscope, because with a microscope you can't see the electron, and certainly you can't keep up with the electron. But what you can do is to say, okay, I have certain constraints. I know that electrons must occupy, you have a certain number of laws, like there can be two different spins in the same place, there can be more than two different electrons in the same orbital, because they have to have inverse, I don't remember the stuff anymore, but anyway, they have to have inverse spin. Then they have to take, there are the energy levels, so you have a bunch of rules. And then you set up the equations that allow you to find the probability starting from these constraints, and you end up with this sort of stuff. So these are results of an optimization process, basically, a mathematical optimization process. So it's all math. Nobody has ever seen the electrons in that position, okay? But it works. It's a model that works. Now, this is actually an interesting set of functions that we use in order to represent an arbitrary function. So we say, if I have a radius, if I have a sound field, and I want to represent it as a linear combination of many other functions, I want to choose a basis of function. And this is a basis of function, and I project the shape, the arbitrary shape, into this basis of functions here. And to me, an arbitrary shape is a linear combination of those shapes there. So we do the opposite, but it's the same function that we use in chemistry, okay? And by using the parameters, we drive, through some processing, we drive a bunch of loudspeakers. And so it looks like this, which you will see in the laboratory later. And you will be able to use these functions to drive a bunch of loudspeakers, and the loudspeakers will pump energy all together in order to recreate an area around your head, like the sweet spot, right? The perfect sweet spot, so you can enjoy the sound field as if you were there. Pretty much like Sheldon does in the Big Bang Theory, except he doesn't hear in 3D, he hears only in, well, not even in stereo, just things. So. Then there's another, this is another lab demo we have in a different lab, where you can use a joystick to move around and go visit virtual spaces and hear the impression, have the impression of being there, activating, controlling with the joystick. It's like an audio game, right? You can navigate into mazes, you can navigate into a 3D maze using basically acoustic control over things. So why don't I just live? Oh wait, one thing I want to show you. Last thing, and then I'll leave you to them. They're much better than me at talking. So there is one other thing that is possible. You can also model in real time how the environment responds to stimulation, to an acoustic stimulation. And there are techniques for doing that. They're called ray tracing. Have you ever heard of ray tracing? So when you see an animation movie, there is visual rendering that is done. You see that there is brightness, there is haze, there are particles in between. So when you see an animation movie, the rendering is a process that makes the whole thing look good. Now, you do the same thing in audio. In audio, you do sound field and you do acoustic rendering using ray tracing. We developed something that is kind of fun to watch in action. So let me show you this quick video on acoustic modeling. It's the only system that in existence that does acoustic rendering in real time. So you are in 3D in a 3D space. You're moving around using the mouse, and well, right now you can't see what I'm talking about so far. It is only showing how two surfaces see each other, the visibility between two different surfaces. But you can define like a loudspeaker and a listening point, and see where all the rays, acoustic rays, how they bounce around in the whole environment. And it's going to be right here. So, and right now it's set to model up to the 5th order of bouncing. So it can model up to 5 bouncings, but you can do also 100. It doesn't matter. And when you move the loudspeaker or the microphone, the rays are recomputed in real time. That's only one thing that he's showing. It actually is computing the whole sound field in real time. And this is done at an amazing speed, because you trace the like 80, 100,000 rays up to the 5th order of bouncing in a matter of 1 millisecond on a single laptop computer using one thread. So not using all the cores, just one core. Okay? How does that work? It works by using a lot of geometry. You need to learn how to do geometry very well. So, you guys like geometry, or you don't like geometry? This is not a place for you. Just let it go. Because most of the stuff you do can really be speeded up using geometry very well. Geometry is what really gets things working in real time. With any commercial software, that kind of stuff will require 10 hours of computation, which are reduced thanks to geometry in 1 millisecond. Okay, that's actually the engine behind everything, every audio game that we're working on and developing right now. But I'm going to leave you to Francesco, who's going to be talking about interesting things.
Only for my student, I forgot to introduce the Professor Augusto Sarti, the responsible of the acoustic laboratory. Thank you again for the very, very interesting presentation. I appreciate for my student also your funny way to explain physics. Thanks.
Well, we try to make it fun. It's easy because it's fun to do this sort of thing. It's not me who's funny, it's the topic that is fun, so it comes naturally.
Buongiorno, io sono Francesco e come già accennato il professor Sarti mi occupo dell'analisi timbrica di strumenti d'arco e si tratta di una cosa un po' difficile perché cos'è il timbro? Non è qualcosa che si può misurare con formule matematiche ben definite, è qualcosa di totalmente soggettivo, sia dal punto di vista della percezione che della descrizione. Quindi cercare di catturare il timbro di uno strumento musicale è qualcosa di non banale, che richiede delle tecniche elaborate. Quindi possiamo vedere il timbro come qualcosa di molto astratto e di poco oggettivo, perché gli ascoltatori, per descrivere il timbro di uno strumento, utilizzano parole che vengono dal linguaggio naturale e non relative per forza all'udito. Ad esempio si può sentire parlare di un suono caldo, di un suono rotondo, di un suono brillante, scuro, e sono tutte parole che hanno una base matematica che consente di catturarle automaticamente. Dall'altra parte di questo grafico abbiamo la fisica del suono, quindi abbiamo il segnale audio che possiamo registrare e che contiene migliaia di informazioni oggettive che possono essere ricavate tramite procedure matematiche di elaborazione dei segnali. La cosa difficile, diciamo, è tentare di collegare queste due parti, quindi di istruire una macchina, un programma, a analizzare un suono che devo registrare vogliamo produrre una descrizione che è quella che darebbe un essere umano, quindi una descrizione che si dice ad alto livello. Quindi quello che facciamo per risolvere questo problema è effettuare una serie di registrazioni audio nella camera semianecoica che vedete tra poco, normalissimi, e queste acquisizioni audio verranno utilizzate per fare due cose. Intanto saranno proposte a degli esperti che le ascolteranno e forniranno per ogni strumento registrato una descrizione ad alto livello, quindi diranno questo è uno caldo, questo è uno scuro, eccetera. D'altra parte queste registrazioni verranno usate per estrarre quelle che in gergo tecnico si chiamano feature di basso livello, che sono semplicemente una serie di caratteristiche di proprietà che possono essere ricavate in modo oggettivo dal segnale audio registrato. Quindi, ad esempio, qui citiamo un caso di studio che è l'analisi timbrica, l'impatto sul timbro del processo di verniciatura degli strumenti. Questo è uno studio che abbiamo fatto qualche anno fa e abbiamo voluto studiare come il processo di verniciatura degli strumenti ad arco influisse sul timbro degli strumenti. E quindi per questo studio abbiamo chiesto a una liutaia di costruire apposta uno strumento e di farcelo analizzare in tutti gli step del processo di verniciatura, e per ogni step abbiamo estratto quelle feature di basso livello, quindi descrittori oggettivi del suono, e siamo andati a vedere come questi cambiassero tra un passo e l'altro del processo. Spiego un po' velocemente. Abbiamo visto ad esempio che l'applicazione del primo strato, che si chiama laboratori, produce come effetto quello di aumentare la brillantezza del suono. La brillantezza è uno dei descrittori che possono essere ricavati dall'analisi di un segnale audio. Come vi è stato accennato, per poter istruire un programma a elaborare delle parole del tutto soggettive senza un significato matematico preciso, bisogna trovare un modo di formalizzarle. Cosa vuol dire formalizzarle? Vuol dire renderle interpretabili da una macchina, da un software. E per questo ci viene in aiuto quello che si chiama l'ontologia, che è uno strumento utilizzato soprattutto nell'ambito del web semantico per rendere formale, per formalizzare la conoscenza in uno specificare l'interesse. Quindi abbiamo le basi di dati, ad esempio, che servono per raccogliere dati, e le basi di conoscenza, che si basano sulle ontologie, che invece servono a raccogliere conoscenza e a renderla processabile da una macchina. La nostra ontologia riguarda non solo il timbro degli strumenti e la relazione tra il timbro e la fisica del suono, ma anche per adesso anche tutta la parte della costruzione del violino e dei materiali che compongono lo strumento. Questo perché poi il nostro obiettivo è di formalizzare la relazione che c'è tra la costruzione e le proprietà sonore dello strumento. Quindi questo è ancora un lavoro in fase di sviluppo. Quindi abbiamo accennato prima a come si possa istruire un programma per produrre una descrizione timbrica simile a quella che darebbe un essere umano. Quindi prima di tutto abbiamo voluto capire quali fossero i termini più utilizzati dagli esperti per descrivere un suono, e quindi abbiamo condotto una serie di interviste in cui abbiamo chiesto agli liutai di Cremona, che sono tantissimi, quali fossero i termini più usati da loro e quale fosse il loro significato e la relazione tra questi termini, quindi quali fossero ad esempio sinonimi non contrari. Qui si può vedere un esempio. Dopodiché abbiamo proposto loro un test in cui abbiamo fatto sentire le registrazioni di vari violini che abbiamo registrato, tra cui anche violini della collezione storica del Museo, quindi violini pregiatissimi, e per ciascun violino abbiamo chiesto di dare un punteggio da 0 a 10 per ciascun termine descrittivo. Ad esempio, in questo caso si vede la scala che va da chiaro scuro, e i soggetti dovranno posizionare i violini che sentivano su questa scala. Dopodiché abbiamo utilizzato delle tecniche che si chiamano di machine learning, di apprendimento che consistono nel prendere in ingresso le annotazioni che derivano da questo test percettivo che abbiamo fatto e contemporaneamente anche le feature di basso livello, quindi quelle che si possono estrarre automaticamente da un segnale audio. Queste tecniche consentono di costruire un modello che dovrebbe imitare il modo in cui la mente umana produce una descrizione a partire da un suono percepito. Quindi questo modello cosa ci consente di fare una volta costruito? Ci consente di analizzare un qualunque altro suono e di produrre automaticamente una descrizione ad alto livello, quindi ad esempio dire quanto questo suono è chiaro, quanto è scuro, che è appunto una cosa che è piuttosto particolare, non banale. Quindi qui ci sono alcuni esempi, magari quello più interessante è questo, che mostra come possiamo usare un confronto, diciamo, per un violino storico e un violino moderno, quali sono le annotazioni, quindi le annotazioni fatte dagli umani, dai soggetti umani, e qual è la predizione fatta dal sistema per ciascun descrittore. In questo caso li abbiamo messi a questa disposizione circolare per facilitare la visualizzazione. Quindi è un sistema che può funzionare e che anzi funziona abbastanza bene. Lascio la parola ad Antonio per quanto riguarda la parte di misure acustiche.
Buongiorno a tutti, siamo all'ultima parte descrittiva, poi lascio un po' all'esplorazione del laboratorio e alla visione della camera anecoica con la DNA spaziale. Vi racconto un attimo come si misura la cosiddetta radianza di uno strumento musicale, quindi in particolare dei violini. Poi avete già visto una presentazione precedente questo grafico che è appunto il pattern di radianza che ci dice come l'energia acustica si distribuisce nello spazio, in tutto lo spazio tridimensionale attorno allo strumento. Perché è importante misurarlo? Per esempio ci dà indicazioni riguardo a quali sono le direzioni di emissione del suono che sono quelle le preferite del violino, quindi sapendo qual è la direzione preferita del violino ci permette di capire come posizionarci ad esempio davanti al pubblico, oppure ci permette di capire come lo strumento interagirà con l'ambiente in cui lo stiamo suonando, quindi come ci dobbiamo posizionare nell'ambiente per ottenere il suono migliore possibile. Ci siamo anche chiesti quali sono i fattori che determinano diversi diagrammi di radianza. Tenete presente che ciascun violino ha un diagramma di radianza molto diverso da questo, ognuno avrà il suo particolare, quindi ogni violino sarà caratterizzato da un preciso ma incognito finché non lo misuriamo patto di radianza. Sono tantissimi fattori che determinano, possono essere la forma geometrica, i materiali che vengono utilizzati, eventuali interventi di restauro, qualsiasi modifica, il tempo che passa, perché uno strumento è qualcosa che vive dal momento in cui è costruito, è una cosa viva, quindi cambia le sue caratteristiche durante il tempo. Tutto questo determina l'impatto di radianza, per cui è interessante misurare. Il sistema che abbiamo sviluppato prevede che il musicista è libero di muoversi, ed è quello con cui accennava Augusto in precedenza. Non vogliamo che il violino sia suonato da uno strumento meccanico, né tantomeno vogliamo vincolare il musicista a essere fermo in qualche posizione, che potrebbe risultare scomoda e non naturale per una normale esecuzione. Il sistema si compone di un po' di parti che andiamo a vedere un po' più nel dettaglio. Abbiamo innanzitutto due camere acustiche che non sono nient'altro che una collezione di microfoni. Come diceva il professor Sarti, ne abbiamo tantissimi e abbiamo deciso di usarli in questo modo. Abbiamo due disposizioni su griglie rettangolari di microfoni che vanno a catturare il suono che viene prodotto dal violino mentre è suonato dal musicista. Abbiamo un minimo di sensori che sono incollati, sono solidali al violino, che sono un microfono di prossimità che ci indica il suono emesso dalla sorgente, e un sensore che è appoggiato sulla mentoniera, che è semplicemente il supporto per il violinista che è a contatto col collo del musicista. Questo è un sensore che ci permette di capire in ogni istante di tempo qual è la posizione, qual è l'orientamento del violino nello spazio, perché è un dato di cui bisogna tenere traccia. Si chiama sensore giroscopico, ci misura l'angolo ad ogni istante di tempo. Sono spaventati, vi prometto che è l'unica formula che vediamo. Descriviamo in linea di massima qual è la procedura per misurare il nostro pattern di radianza. Immaginate per ogni istante di tempo che il violinista suona davanti ai microfoni, cosa dobbiamo fare? Bisogna misurare l'energia acustica che vediamo su ciascuno dei microfoni, ma dobbiamo anche sapere da che direzione il violino emette rispetto a ciascuno dei microfoni. Quindi sapendo la posizione, sapendo l'angolo e sapendo l'energia acustica che viene misurata dai microfoni, possiamo calcolare il nostro pattern con questa formula che tiene conto di tutti questi termini. Abbiamo l'energia acustica direzionale, abbiamo un termine che dipende dalla posizione del violino, quindi è la distanza tra il violino e ognuno dei microfoni, e un termine che è l'energia emessa in prossimità del violino. Siccome questa non è costante, dobbiamo bilanciare il tutto rispetto a questa grandezza. Qui abbiamo un esempio, posso farlo partire, è un video che mostra come il pattern di radianza viene costruito in maniera incrementale. Mano a mano che il violinista produce dei suoni e si muove nello spazio, il sistema, cosa abbiamo detto, riesce a catturare la posizione e l'angolo del violino nello spazio, e abbiamo i microfoni che misurano l'energia. Quindi per ogni istante di tempo riusciamo a ricostruire una parte del diagramma di radianza, e questo appare mano a mano che il musicista si muove davanti alle nostre camere acustiche. In conclusione voglio farvi vedere i risultati su uno strumento illustre che avete visto probabilmente questa mattina al Museo, che è il Cremonese 1715, col suo pattern di radianza. Come vedete, il pattern di radianza è una funzione che è definita sullo spazio tridimensionale. Possiamo vederlo sotto forma di questi diagrammi a forma di sfera, che però modificata, il raggio della sfera per i diversi angoli viene modificato dalla particolare intensità emessa dal violino in quella direzione. Si vede che partendo dalle frequenze molto basse, ad esempio vicino a 300 Hz, e salendo in frequenza per frequenze più alte, il pattern di radianza si complica, diventa sempre più articolato e complicato, sempre meno prevedibile. Questo è vero per tutte le corde che vengono pizzicate o archettate, come dire. Questa è la corda del Re, questa è la corda dell'A, ma quello che è importante vedere è che questo particolare violino presenta, guardate i diagrammi in fondo, che sono una sezione praticamente sul piano orizzontale del diagrammi sferici superiori. Vedete che c'è sempre un punto a maggiore energia intorno ai 45 gradi, riuscite a vederlo? Questo è vero un po' a tutte le frequenze, questo corrisponde esattamente a quello che vi diceva il professor Sarti in precedenza, che il Cremonese 1715 ha una direzione preferita di emissione attorno appunto a questi 45 gradi, che è il punto dove va posizionato il microfono per avere il miglior suono possibile. Sapendo questo, il musicista può anche inoltre rivolgersi verso il pubblico mostrando questa particolare direzione, che è quella principale di questo violino. Questi studi vanno un po' a validare quello che importanti musicisti conoscono ma non hanno mai misurato, sono stati solamente per esperienza e per il culto. Un'altra cosa che accennava il professor Sarti è sempre legata al pattern di radianza, ma anche un pochino legato a quello che vi ha raccontato Francesco, che è l'estrazione di descrittori dal suono. descrittori, questo efficio, possono essere estratte anche per ciascuna delle direzioni, esattamente con la tecnica che abbiamo visto prima per misurare il pattern. Qui abbiamo calcolato un descrittore che misura la brillantezza, che è chiamata brightness in inglese, e se vedete quella macchia gialla nel diagramma in alto a sinistra, corrisponde esattamente a quella direzione di emissione principale dello Stradivari in Cremona 1715. In quell'esatta posizione il violino ha il miglior suono possibile, quindi a maggior ragione in quella posizione ci andremo a mettere il microfono, oppure da quella direzione faremo proiettare lo strumento verso il pubblico. Direi che siamo arrivati in fondo. Ringrazio tutti e probabilmente ci organizziamo in 2 gruppi separati, da 20 persone, per andare a visitare il laboratorio, il primo gruppo, e la camera anecoica dove facciamo gli esperimenti e vi faremo sentire qualcosa di audio tridimensionale. Grazie ancora.
This is just one of 3 laboratories that we have. The audio laboratories are actually 3. One is in Como. It's called the Sound and Music Computing Lab. And we have the Image and Sound Processing Lab in Milano, and this Musical Acoustics Lab. These laboratories are also part of an interdepartmental laboratory called the Sound and Vibration, Polimi Sound and Vibration Lab, which includes also the laboratory of acoustics and energy department, which includes a full anechoic chamber, and the laboratory in mechanics. So it's probably now definitely the largest laboratory in Italy for research in acoustics, and it's becoming one of the largest ones in Europe. So it's if you guys are interested in visiting the other laboratory, let me know, and we'll be happy to show you around and share with you the other laboratories. They're obviously all related to the activities we do here. Here, the focus of these laboratories remains with the musical instrument and the listening environment and musical acoustics in general. The others are more like space-time processing for advanced audio applications, music production, music information retrieval, and other aspects of the sort. But you know, the basics are still the same. Now let's be practical. Now there are about 40 people, and we can't go all in the same place because of security reasons, safety reasons more than security. So how about if the first groups, which includes also the students of my course, and half of the class goes to, for example, in the anechoic chamber, or goes with me, or let's say that we go into the lab, and everyone else goes in the anechoic chamber together with Antonio. So Francesco and I go with my students and half of this. I don't know what the best way of splitting up in 2 for your class is. Come possiamo dividerci?
Così come sono.
Facciamo un taglio a metà, così, va bene. Quindi questo gruppo qua alla mia sinistra, alla vostra destra, viene